We're going to be looking at parametric equations, and in particular we'll be looking at sets of parametric equations. Parametric equations allow us to look at three variables without introducing like a three-dimensional coordinate system. So for instance, we could have a variable t. T usually represents time, and if we have this variable t, it would give me an idea of where I was on a particular curve at time t. So it allows us to keep the x and the y involved and then that time t as well. So for an example, we might have a set of parametric equations of x equal negative t minus 4 and y equal 4t plus 1. So you can see that we have two variables, x and y. They're both defined based on t. So what's happening here then, t is my independent variable and then x and y are my dependent variables based on this value of t. Now usually parametric equations have some sort of a restraint or something involved in terms of a restriction for one of the variables x, y, or t. And for this particular example, we're saying t is restricted from negative 10 to positive 10. So this is kind of our setup that we're starting with, is our set of parametric equations and then also our restriction here. So the first thing we want to do is we want to think about plotting some points. The easiest way to plot points is to go ahead and start with choosing some value of t, because like I said, it's our independent variable. And then once those values of t are chosen, we can go after values for x and y. So to graph, the best thing to do is to probably plot points. So as we start to plot points, we should probably have a table of values. So when I create a table of values, of course you can do horizontal or vertical. I look at values of t and then I determine x and y. Now I don't want to just randomly start looking at some values of t. I want to go in order because we also have to know one other thing about this, and that's the direction. What type of orientation it has, and I'll show you what that means in a moment. But we want to start at the left and go toward the right. So as we start at the left, and we don't have to plug in every single point between negative 10 and positive 10 or even the integer values, I can just choose a few and go through here. So I might choose negative 10, negative 5, 0, 5, and 10. So if t is negative 10, I would come up here and plug that in. Minus a negative is the same as a positive 10. 10 minus 4 would be 6. So that's where we would start. So negative 10, 6. Then I'd plug in a negative 5. Minus a negative 5 is the same as a positive 5. 5 minus 4 is 1. Now these are not ordered pair. We need to have our y value before we can find our ordered pair. T is 0. If I plug 0 in here, 0 minus 4 is a negative 4. If I plug in 5, negative 5 minus 4 is negative 9. And if I plug in a 10, negative 10 minus 4 is a negative 14. Okay, so now I'm going to do the same thing for y. I'm going to take negative 10 and plug it in. I'll have negative 40 plus 1 is a negative 39. If I plug in a negative 5, I have a negative 20 plus 1 is a negative 19. If I plug 0 in, 4 times 0 is 0. 0 plus 1 is 1. And if I plug in a 5, I have 5 times 4 is 20 plus 1 is 21. And if I plug in a 10, I have 40. 4 times 10 is 40 plus 1 is 41. Okay, so these are my ordered pairs now as I read down the x and the y column. So our scale is going to have to be pretty radical here. It's going to go clear down from negative 39 up to positive 41. And then my x values will go from negative 14 to positive 6. So I can't, or I won't, I should say, draw a Cartesian coordinate system with tick marks for each one of those. We're just going to have to kind of scale this a bit. So first of all, I'll go tick marks by 10 on my x and y axis. So 10, 20, 30, 40, negative 10, negative 20, negative 30, negative 40. And then on my x scale, it looks like to me I could go by 2's pretty easily. So 2, 4, 6, 8, 10, negative 2, negative 4, negative 6, negative 8, negative 10, negative 12, negative 14. Okay, so let's go ahead and plot these points. So one is 6, negative 39, so 2, 4, 6, and then negative 39 would be almost down here to the negative 40. So there's 6, negative 39. Okay, and now I need 1 and negative 19. So here's 1, here's negative 20, so negative 19 would be right about there. So that's 1, negative 19. Okay, and then I have negative 4, so negative 2, negative 4, 1. That's going to be barely off the line here. So this is the point negative 4, negative 1, or sorry, negative 4, positive 1. And you kind of get the idea here. Now if I connect these points, whoops, kind of got squirrely there at the end. And then my last one would be 10, or sorry, negative 14, which is clear over here, and then clear up here at 41. Now I want you to notice that we don't have arrows on the ends of these lines because our domain is restricting us from x equal 6 on my positive side to x equal negative 14 on the negative side because my t values are restricted between negative 10 and 10. So these are endpoints, they're not arrows. These do not continue on indefinitely in either direction. So here's our line. Now this is a quick curve sketch. These are my points that I've plotted. And remember, I did these in order specifically from negative 10 to positive 10. So we're missing one thing here, and that's the positive orientation, meaning what is the direction of increasing t? So direction of increasing t is I would start at the negative and move to the positive. So direction of increasing t. So what this means is, and this would have to do with time and how time is moving here, is time coming from this point up here and moving down, or is it coming from this point and moving up? So if we look at this, I'd start over here at negative 10, 6, or sorry, negative 10 for t, which produced the point 6, negative 39, so that would put me here. So I moved from 6, negative 39 to 1, negative 19, so I moved up from here to here. So this is the direction of increasing t. So as t is increasing, I'm moving in this particular direction. And so the positive orientation here would be left, meaning my graph is moving to the left. So positive orientation equals left. And so the reason we didn't just randomly pick some t's in any random order is we needed to look at how the graph was changing or increasing as we went from the smallest value to the largest value. So those are all important things to keep track of while you're working with a set of parametric equations. So the line that we've drawn is the line represented by this particular set of parametric equations. Now one other thing we haven't done is we haven't rewritten this in terms of x and y. So we could eliminate the parameter t and equate and write this in terms of x and y. Now this is just some nice algebraic substitution. So we started with x equal negative t minus 4 and y equal 4t plus 1. So what I'll do is I'll choose one of these to solve for t and plug into the other one. Now the important thing to keep in mind is we usually like y equal when we're trying to graph something, you know, like y equal 2x plus 4 or y equal x squared. So I like to always leave my y equal and then plug in for my t here. So if I solve this one for t, I'd add the t to both sides and then I would subtract the x. T would equal negative x minus 4. And then simplifying this expression, I'd have y equal negative 4x minus 16 plus 1, and I'd have y equal negative 4x minus 15. So this is the equivalent rectangular xy graph. Now one thing that this doesn't take into account is the fact that I'm limited for my values of t. But I do know my values of x. My values of x would go from negative 14 to 6. So if we had to write a restriction here, I would say x would go from negative 14 to 6. And I get that from looking right here. My smallest value is negative 14 all the way up to 6. Now notice I directly plugged in both endpoints to determine that. Okay, so that's an example of working with a set of parametric equations. One other thing that we can look at, because we've got quite a bit of information here, the slope of the tangent line is negative 4. That basically tells me then if I come and look at this line, the slope had better be negative 4 because it's a line itself. I could find the derivative. I could determine dy dx. By taking the derivative of my y equation with respect to t over the derivative of my x equation with respect to t. So y is equal to 4t plus 1, so that would be the derivative with respect to t of 4t plus 1 over the derivative with respect to t of my x equation, which is a negative t minus 4. So the derivative of 4t plus 1 is 4. The derivative of negative t minus 4 is negative 1. So that tells me then that my slope, or my derivative, however we want to interpret that, is equal to a negative 4. And that matches this information perfectly down here, negative 4 as well. Now up here, one more time, as we're looking at this, it doesn't matter what value my t is, because once I take my derivative, there's no t left. So that tells me that my slope is equal to negative 4 anywhere, no matter what value of t I'm looking at. So once again, we've looked at quite a few things with one problem, with one set of parametric equations. But that's, a nice little rundown of parametric equations, graphing parametric equations, taking derivatives and finding slope, and then talking about right or left positive orientation with parametric equations as well. Now when we're working with parametric equations, they're not always these nice lines that we just looked at. We can also have other things like transcendental functions, and we could also have squared terms as well. So let's consider another set of parametric equations, and we'll do something a little different with this set. So to get started, our set of parametric equations will be x equal t plus 3 quantity squared and y equal t plus 4. So this is what's a little bit different about this one, is that up above they were both linear. Now I have a quadratic and a linear combined. So it'll be kind of interesting to see what these look like. Now as we're working with these quadratic equations, again, a lot of times I have to have a restriction or one will be provided. And the restriction here, again, is the same as our last one, negative 10 to 10. So there's what we're looking at for my set of parametric equations. So the first thing I'd like to do is to rewrite this. And it doesn't really matter what order we do these in, but I'm going to go ahead and rewrite this. So to get started, I have x equal t plus 3 quantity squared, and I have y equal t plus 4. Now as we're working through this, usually we like y equal, so I'd usually keep this equation and I'd substitute in for this t. But if you look at this, substituting in for this t isn't really all that easy. I could do this pretty easily by just going ahead and taking the square root of both sides. So again, it's not as obvious, but I think it'll be easier when we can graph something as a y equal. So let's work from this one, and we'll go ahead and take the square root of both sides. Now if I take the square root of x, remember I have two roots there, plus or minus root x equal t plus 3. So that means I, again, took the square root of both sides, so don't forget the plus or minus. And then solving for t, I get t equal 3, so here's my 3, plus or minus root x. Oh, and this 3 I subtracted over, so I need to make sure I have a negative there. So negative 3 plus or minus root x. And then what I'll do is I'll bring that down and plug it directly in. So I get y equal t, which is negative 3 plus or minus root x plus 4. And then combining my like terms, 4 minus 3 is 1. So I have y equal 1 plus or minus root x. So really I have two equations there, one plus root x and one minus root x. So this is my parameters in terms of x and y. Now one thing we haven't really looked at here was the effect of the parameter t goes from -10 to 10 on our outcome here. So we'll see that in the table in a moment, and then we can update this with any domain restrictions if we have to. Okay, so next let's go ahead and graph this and then look at whether it has a positive, with our positive orientation, whether it has a right or a left. So let's go ahead and graph this. Best way to graph is to go ahead and look at some xy values, given values of t. Now if I wanted to, I could graph directly from here. I could graph one part that was 1 plus root x and one part that was 1 minus root x. I'm going to go ahead and graph off my parametric equations and then also look at the domain of my values for t. So again, these go from -10 to +10. But when I'm looking at the -10 to +10, I can see I'm going to get some pretty big numbers here, and that's fine, but I need to make sure that I check enough values that I get a good idea of what this is going to look like. And again, I'm traveling as increasing t, so increasing t. Okay, so as we're increasing t, if I plug in -10 into x, or into the equation of x for t, what's -10 plus 3? That would be -7. -7 squared is 49. And I'm just going to go ahead and plug all of these in. -5 plus 3 is -2. -2 quantity squared is 4. This would give me 9. 5 plus 3 is 8 squared is 64. 10 plus 3 is 13 squared is 169. And then for my y values, if I plugged in a -10, -10 plus 4 is a -6. -5 plus 4 is a -1. If I plug in a 0, 0 plus 4 is 4. If I plug in 5, 5 plus 4 is 9. And if I plug in a 10, 10 plus 4 is 14. So these are my ordered pair, and it also kind of has this natural restriction here. Now it looks like to me, when we looked at this equation, we might look at this and say, oh, values of x, they could be anywhere from 0 to infinity, because I can take the square root of 0 or any positive number. But as we look here, because my restrictions on t, it looks like I'm going from 49 to 169. So there's really quite a bit different. Really, there's quite a bit more different things going on here. Okay, so let's go ahead and graph that. Actually, I want to check my points first. Some of those look a little bit big. So I plug that in. Yeah, they look fine. Our scale is going to have to be, it looks like, more in the positive x direction. So when we draw our coordinate system here, looks like my y values don't go too huge. Okay, so this 169, so let's kind of come out here to 200, we'll say. So there's 100, there's 50, 150. So kind of an extreme scale. Now my y values go down to -6, so I'm going to go down by -2, -4, -6. And then up here 2, 4, 6, 8, 10, 12. A little bit more here, 14. Okay, so let's go ahead and plot some points. So I have 49, -6. So here's 49, here's -6. So that's kind of the start of my graph. There's no arrow. This is where my graph starts. Then it goes up to 4, which would be, you know, clear over here close to the axis, -1. So I'm going to say right there. So there's 4, -1. Then we have 9, which we'll say is somewhere right here, 4. And then 64, so he'd be 75. So here's 64, 9. and then 169, which would be right about here, 14. So it looks like to me our graph something's happening right in here. Now I didn't plug in every possible value, but I'm kind of curious now, what would have happened if I would have plugged in a -3 right here? So I'm going to sneak a -3 in right here. So -3. Well, if I would have plugged a -3 into x, I would have gotten 0 back out. -3 plus 4 would have been 1. So this would have been the ordered pair 0, 1. So this is kind of the vertex of the parabola. So that's just an extra point that helps us see what's going on here. It doesn't ever cross over into the negative x values, which totally makes sense, because negative x values wouldn't make sense for my parametric or for my non-parametric form, for my rectangular form. So if I look at the direction now, I can see that I'm starting here with my smallest value of t and I'm increasing, and this looks like it's going to the right. So as I look at this, this is a parabola that's opening to the right, and if I have to show my arrows to show that positive orientation, just like on the problem I did before, I said it positive orientation is left. This one, positive orientation is right. Because my graph and my arrows, as time increases, is moving to the right. So this is not a function. It doesn't pass the vertical line test, but it is creating this shape, a parabola on its side, that is increasing in that positive direction. So those are a couple different examples of graphing parametric equations, looking at orientation. We can also do this with trig functions. With trig functions, one of the things that you might want to remember is your trig identities, particularly sine squared plus cosine squared is 1, and keeping in mind how you graph and how those relate as well. Okay, let's go ahead and look at kind of working a problem a little bit backward. Instead of being given parametric equations, let's go ahead and try and write some parametric equations. And it'll be, of course, more fun with a trig function. So let's involve a trig function. Let's find parametric equations. Actually, let's do a problem before this that'll help us with this one, so kind of give us some frame of reference. So we'll do this one next. So for this one, let's go ahead and start with a set of parametric equations that are trig functions, and so we can look at working with them and kind of getting an idea for that, so when we work backward we have a little bit more background. So for parametric equations, I have x equal 2 cosine of t. Always put parentheses around the arguments of your trig functions, and y equal 2 sine of t. And I also have a restriction. My restriction is t goes from 3 pi over 2 to 5 pi over 2, and if you notice, this is a very specific direction for t, so we have to be careful about that. So first of all, we're given some information here. It tells us that it's either a circle or part of a circle. So this is circular or an arc from a circle. And we need to find the center of this arc or this circle and the radius. And we need to indicate its direction, right or left. And I guess we could also write this in rectangular form. We don't have to, but let's go ahead and do that as well. So again, you could work this whole problem without putting it in rectangular form, but it's usually easier if we do. Okay, so first of all, let's go ahead and get started by plotting some points. And then after we plot some points, we'll look at a bit of a graph and try and get that orientation or the direction down. And then we'll talk about its radius and its center as well. Okay, so let's go ahead and graph this to begin with. Now as we graph through this, I'm going to choose values for t, and then I'll have values for x and values for y. Now I need to make sure I start at the smallest and increase on my t, so this is going to start 3 pi over 2. and it's going to go to 5 pi over 2. So in between those would be something like, okay, we could be at 3 pi over 2, we could be at 0, and we could be at 5 pi over 2. Now if I wanted to choose negative pi over 4 in here, or actually it'd be 7 pi over 4 or 11 pi over 6, I could choose all sorts of different angles as well. But I want to just kind of stick with the endpoint for my beginning and the endpoint for my ending, and just choose a value in between. So if I plug t equal 3 pi over 2 in for x, the cosine of 3 pi over 2 is 0. 0 times 2 is 0. Okay, cosine of 0 is 1. 1 times 2 is 2. 5 pi over 2. The cosine of 5 pi over 2 is the same as the cosine of pi over 2, because 5 pi over 2 is basically at your 90-degree angle. Cosine of 5 pi over 2 is 1. 1 times, or actually it's 5 pi over 2 is 0. 0 times 2 is 0. Now let's do the same thing down here. The sine of 3 pi over 2 is negative 1. Negative 1 times 2 is negative 2. The sine of 0 is 0. And the sine of 5 pi over 2 is 1. 1 times 2 is 2. So again, this is my direction of increasing, so I want to keep that in mind. Now as we graph this, I have values that are just basically on my rectangular plane here. And these look like pretty decent numbers to work with in terms of my scale. So I'd start off with 0, negative 2, that's right here. Then it would go up to 2, 0. And then it would end at 0, 2. So this is the movement that I'm making here. It's supposed to look circular. It almost doesn't because of my goofy scale. It almost looks elliptical, but it is circular because I can see I'm moving up 2, out 2, down 2. Now the direction that I'm moving, I'm starting down here, and then my next point is in this direction. So again, it's important that you be able to put the orientation here, and this would be definitely left. Okay, the overall arc would be left here. Now, when we talk about left, it almost looks like it's heading right and then switching left, so you kind of almost look at the end behavior. But a lot of times when things are circular, when I talk about their positive orientation, instead of saying right or left because these look circular, I talk about whether they're clockwise or counterclockwise. Now this one would be counterclockwise. So that might be easier to say that instead of right and left, because you can see that it does change. So this has counterclockwise movement. So there's a couple things there, and we can talk about its center. The center of this arc would be 0, 0, and the radius is definitely equal to 2 units here. So I think we ran through everything except for rewriting this in rectangular form. So in rectangular form, I need to remember some trig. So again, just to have these copied down, I have x equal 2 cosine of t and y equal to sine of t. So what I'm going to do here is I'm going to remember a trig identity, and that was that sine squared, I'm going to say, of t plus cosine squared of t equals 1. So if I solve this one, sine of t, for sine of t I get y over 2. And if I solve my other one for cosine of t, I get x over 2. So again, order doesn't matter whether we add sine squared plus cosine squared or cosine squared plus sine squared. Sine squared is y over 2, quantity squared. Cosine squared is x over 2, quantity squared, equal 1. So I have y squared over 4 plus x squared over 4 equal 1. Multiply through by 4, and I'll have x squared plus y squared equal 4. So that's our nice equation of a circle. Radius of 2, because this is r squared, centers at the origin, and so that's, you know, my rectangular form. Now when I look at this, my restriction on t was 3 pi over 2 to 5 pi over 2. When I come over here, I don't really have a restriction, and it looks like if I graph this, this would create a full circle. So I do need to have some sort of a restriction. If you look at your values of x, it looks like x went from 0 to 2 here. that was my only values of x that are possible given these restrictions on t. I never had any negative values of x. So I think to be thorough with this one, we need to also include a restriction. So x was between 0 and 2. And that would produce this arc that we have right up here. Okay, so given that background with some trig functions, let's go ahead and kind of work at a problem a little bit backward. So for this one, we want to write the parametric equations that when they were graphed, they would represent a circle, not just an arc, but a circle. Let's go ahead and put it center at the origin to make this a little bit more straightforward. And for this one, let's have a radius equal to 8. Okay, so let's start with that. Well, in order to talk a little bit more about this, remember up here we talked about counterclockwise movement. Down here, let's go ahead and talk about clockwise movement. So let's go ahead and add a little bit here. So we want this with clockwise generation. That means when we get done and our arrows go in, they'll go clockwise. Okay, so if we talk about a center, we know the general form for a circle is x minus h quantity squared plus y minus k quantity squared is equal to r squared. So in our case, hk, which is our center, is the origin, so that's 0, 0. In our case, r is the radius, and our radius is equal to 8. So filling this in, this would look like x minus 0 quantity squared plus y minus 0 quantity squared equals 8 squared. And of course x minus 0 is just x, so I have x squared plus y squared equals 64. So there's kind of where I can start. Now I want to get this in terms of x's and y's. So what I'm going to do is I'm going to divide through by 64. And then I have my x's and y's, so I have x over 8 quantity squared plus y over 8 quantity squared equals 1 squared. 64 divided by 64 is 1. And I'm just going to rewrite that as 1 squared just so we see that that's radius squared. Okay, so now as we keep working, we know that x and cosine are related. So using the same logic as we did kind of in our last problem that we worked, let's go ahead and look at cosine of t is equal to x over 8 then. And sine of t is equal to y over 8. And then again, we know cosine squared of t plus sine squared of t equals 1. So that's why we wanted this 1 over here, so we could just plug directly in. Cosine squared was x over 8, so this is x over 8 quantity squared plus y over 8 quantity squared equals 1. So if we do that direct substitution, you can see that we get right back where we started. So we don't have any mistakes here at all. Okay, now we want this in terms of parametric equations. So I think we almost have it here. For parametric equations, if I solve this for x, I'd get x equal 8 cosine of t. And here I'd get y equal 8 sine of t. So here's my parametric equations. And then if we also talk about some sort of restriction, we're going clear around the circle. We haven't graphed this yet, but it says we have an entire circle. So I think we need to make sure we go from 0, all the way to pi, all the way around to 2 pi to make sure we get that full spin. So let's make sure t goes from 0 to 2 pi. So here's my parametric equations. This is my rectangular before I divided through. Here's my parametric. So that worked very slick. Okay, so now let's go ahead and look at graphing this. Now we can graph from either the rectangular, or we can graph from the parametric, or just simply from the description. Well, from the description they said we have a center at the origin, and we have a radius of 8. So I'm just going to tick off some marks here and say these are 8. And then we'll do our best just to fill this in perfectly, and that is a circle. Doesn't look like it, but it's a circle. Now the next thing we need to know is we need to look at this and we need to say, okay, this needs to be generated clockwise. So when I get done, this is how my curve should be moving. So I need to check to make sure that that's actually happening. And again, this should be clockwise movement. Okay, so I'm going to choose values of t because I want to double check this. And then I'll have x, and then I'll have y. So let's start at 0 and go to pi over 2, pi, 3 pi over 2, and 2 pi. And let's see what our movement is. So if I plug 0 in for my x, cosine of 0 is 1, 1 times 8 is 8. So that starts out at 0, 8. So I'm starting in up here. Actually, that's wrong. I was reading this as x and this is y. I need to plug this in for 0 here. The sine of 0 is 0. 0 times 8 is 0. So it's starting right here at 8, 0. Now, I want it to move up in this direction. Actually, I don't. I want it to move clockwise. So all my reds are wrong here. I want it to move clockwise. So let me get those fixed. So clockwise would be this direction. Okay, so 8, 0 would start right here. Now let's see where my next point moves to. If I plug pi over 2 in up here, the cosine of pi over 2 is 0. 0 times 8 is 0. And then if I plug pi over 2 in here, the sine of pi over 2 is 1. 1 times 8 is 8. So that's the point 0, 8. So I move from here to here, which is counterclockwise. So that tells me that these are wrong. 8 cosine t and 8 sine t are wrong. Well, a quick fix for this is to just negate the argument of your trig function. Okay, so this didn't work. So this is if we were using 8 cosine of t, x equal, and y equal 8 sine of t. It didn't work, so we have them wrong. So let's go ahead and try something else. Let's try x equal 8. We want it to rotate the other way, so I'm going to negate the argument of my trig function. Okay, and let's see what happens then. Let's go ahead and plot. We just need to plot one point basically. So we have t, x, and y. Actually, we need 2 points. So we'll start with 0 and pi over 2, and we'll see what happens. So if I plug a 0 in, cosine of negative 0 is cosine of 0 is 1. 1 times 8 is 8. Now as I plug in 0 here, sine of 0 is 0. 0 times 8 is 0. So I still start at this point. Now my next point is going to be important. As I plug pi over 2 in here, negative pi over 2, the cosine of negative pi over 2 is 0. 0 times 8 is 0. So this is looking identical. Let's see what happens. But as I plug sine of negative pi over 2 in here, I get negative 1. Negative 1 times 8 is negative 8. And this is the point 0, negative 8. So right now, I have that correct rotation. So these are the correct equations that I need. And again, you have to check that to be sure. So up here, what we need to do is we need to change this to a negative t to compensate for the clockwise rotation. And the only way you would catch that, you can memorize some more formulas up front if you wanted, but the only way you catch that without memorizing those extra formulas is just to go ahead and plot a few points to see what's happening. So again, the red, the negative, account for the clockwise rotation. So, kind of nice to be able to work with trig functions again. Now we talked about derivatives already and slopes of tangent lines, so none of that has really changed in terms of derivative and finding slope. Remember, slope is just your first derivative, and if we're talking about dy dx, then what I'm doing then with dy dx is I'm taking the derivative of the y with respect to t divided by the derivative of x with respect to t. So this next one we're going to be working a bit backward as well. We have a curve, and we're going to call it a complete curve. Now when we say a complete curve, that means there's no restrictions. It's the entire curve that's represented. And we have the complete curve x equal negative t cubed plus 4t. Actually, that's not what I wanted. We want to start with x equal negative y cubed plus 4y. So we're starting with the rectangular. We want to rewrite this in parametric form. And as we're rewriting this in parametric form, we also need to consider any restrictions that we might have. Now the easiest way to rewrite this in parametric form is we need to choose something for x and something for y. And the easiest thing to choose usually, we don't want to choose anything for x here. We want to choose y and substitute in y equal t. Because if we do that, we get a nice little parametric curve, y equal negative t cubed plus 4t. And there's my set of parametric equations right here. And it looks like to me there's no restrictions, so t can go from negative to positive infinity. Now to graph this, you would have to plot some points, and then you'd also have to look at the orientation as t increased. Now, and I'll leave that up to you. The graph of y cubed would look something like this. The graph of negative y cubed would look something like this. So that tells me, I'm sorry, x cubed would look something like this. Negative x cubed would look something like this. So if I'm talking about y being cubed, I'm either talking about kind of an S shape for a positive y cubed. Got to get that shape in there right. For a positive y cubed. And then for a negative y cubed, something like that. So again, some familiarity with the different shapes is going to be really important. Now we've already talked about most of these graphs, and we've talked about the orientation. Some of these are really difficult to graph. Some of them are not a nice shape, not a nice parabola, and so on one of the homework problems you're asked to use a graphing utility. So you might have a graphing utility on your computer already, something like MATLAB or Maple. If you don't, you can graph these using Desmos. It's an online graphing calculator. I like Desmos. So for this particular instance, this is the graph of a parametric equation. This is the parametric equation x equal 2 cosine t, y equal 2 sine t. But if you notice, I just write these as an ordered pair, and then I look at any restrictions. So let's go ahead and write out our graph first, and then we'll go ahead and pull in what that looks like. Now again, this one was complicated enough because it's not a 3 cosine t, it's a t cosine t. And unless you graph a lot of these, you probably wouldn't be able to guess that that's what it was going to look like. This is kind of a spiral shape. So here's my parametric equations, and I also have a restriction, t greater than or equal to 0. So I'm going to show you how you would do this in Desmos, and if you're using a different graphing utility, you can just Google graphing parametric equations, whichever utility that is. Now in Desmos, we're going to look at this in terms of an x-y coordinate pair. So x is the first value, y is the second value, but we know from here that x is equal to t cosine of t and y is equal to t sine of t. So this is what I'll graph in Desmos. Now t is greater than or equal to 0, and because t is greater than or equal to 0, basically I'm looking at 0 to infinity. Now I can't put an infinity in here. I can just put big numbers in. So I'll start at some big numbers like 9, and you'll see that this is that spiral shape. And as my numbers get bigger, it spirals out further and further. Okay, but it starts here, and then the spirals to the left or the counterclockwise direction. So you have to make sure you get that correct spiral shape. So I'm going to go ahead and take a screenshot of this. And pop that into the lecture as well. And again, if you have a different graphing utility, that's fine. Just go ahead and Google the directions for that particular graphing utility, and you should be good to go. So working with parametric equations is pretty handy because we have three variables involved. We have x, y, and t. T usually represents time. So when we're looking at these, I don't have anything more complicated like a 3D plane that I'm working with, XYZ plane. I can just, work interchangeably with the set of parametric equations, and then also looking at these in terms of rectangular with particular conditions. Remember, derivatives are pretty straightforward. It's the derivative of the y with respect to t over the derivative of x with respect to t. And then in order to figure out what the derivative is at a particular point, you'd actually have to plug in that value for t. I think we've looked at everything that you will need to work forward through this. It's pretty straightforward. The most important trig identity that we're going to need is x squared plus y squared equals 1, or cosine squared plus sine squared equals 1. That'll be an important one for you to keep in mind. Have fun with these. It's kind of nice to look at some different types of problems.